Recording has started.
Alright, welcome back to EC 3030. Today is the last technical lecture. And before the lecture, here is an announcement regarding the rest of the semester and the final exam schedule. So today we are going to discuss the lecture 20. And then on Thursday, we will have in-person meeting for the last subgroup of the class. The agenda there was to go over the practice exam for the final, and we have already put that into the exam folder under the Canvas. And this Friday, midnight, homework 5 is due. And then next week, Tuesday, we will have a virtual review for the materials that you need for the final exam. And after that, I believe it's Thanksgiving, and then the week after, from Wednesday, December 2nd, noon, to Thursday, December 3rd, noon, you will have the 24 hours time window for the final exam. So this will be similar format as the previous two exams. And we have two sections in the ECE 3030, section A and B. And we have to synchronize the exam time window for both sections because we are going to use the same materials and then the same grading policy. So to keep consistent for everyone, so we have to stick to this schedule. So the final exam will be cumulative, but the emphasis will be the materials after the second meter. Roughly 60% of the grades will be about the lecture 15 and then to the lecture 19. So today, the lecture 20 will not be part of the final exam because today is more like a advanced topic. So we are not going to have that in the final exam. And we will talk about more materials next class and the next week. Then we will review the materials for the final exams. So stay tuned for that. Any questions so far regarding the schedule? No, then we are going to start today's lecture. So this is lecture 20, Advanced CMOS and Industry Trend. So I'd like to have some introduction about the latest technologies that will be probably used in the industry and what will be the future of the industry. So I'd like the students to have something beyond the textbook and get closer to the industry trend. So this is the motivation of this lecture. That's why this is not part of the exam. So this is for your future interests to develop your career if you wish to work on the computer system hardware. This is the recorded material from last spring semester. And let's talk about the CMOS scaling. And actually we have lecture 15 to cover the motivation for the scaling and the historical trend of the scaling. And we have the Dennard scaling law. And then here we're going to give some recent updates for the last few generations that it was used in the industry. So here we show from like 65 nanometer, which was introduced around 2005, to today is like 7 nanometer and 5 nanometer. So here, those are the technology nodes used by the industry. And this chart was taken from Intel. So it's a representation from the Intel's perspective. So here, the 32 nanometer, actually TSMC and other foundries may use 28 nanometer technology node. And then 22 nanometers, other foundries may use 20 nanometer. And Intel actually use 14 nanometer here, and then the other industry use 16 nanometer. So here this is like 10 nanometer, or some company call 11 nanometer. So that means what? Those technology nodes no longer represent the physical gate length, and different companies may have a little bit different gate length in their designs. Therefore, this is more like a symbol for this generation. So some companies may use one gate length, the other companies may use another gate length, but they are close. So this is more like a symbol when we talk about the 28 or 22 or 14 or 16. This is more for the business advertisement purpose. You need to have a name for that generation. And different companies may use different strategies here. But this is a historical trend, and today, I think this year, TSMC is the leading company to announce the 5 nanometer processor, and the latest product, like the Apple M1 chip, is using the TSMC 5 nanometer process. So this is at 2020. And here I just want to introduce some of the key innovations in the transistor technology that was introduced to enable this scaling. So the first one is the high-K metal gate technology that was introduced by Intel at 45 nanometer node, and the other companies followed Intel but introduced at later nodes. For example, TSMC introduced the high-K metal gate at 28 nanometer node. So what is this high-K metal gate? This is regarding the gate stack in the transistor. So in this course, we have learned that here in the transistor structure, we have the gate oxide separating the channel and the gate. So this gate oxide, historically, it was silicon dioxide. And the silicon dioxide has a dielectric constant, or the relative permittivity, epsilon, around 4. But the industry wants to increase the dielectric constant for this oxide because we care about the COX, and we want to have larger COX for many reasons. One of the reasons is the current. Current is proportional to the mu COX, and you have W over L, and you have the other voltage terms here. But basically, current is proportional to this COX. So if you use higher K value, higher epsilon, then you are going to have larger currents. And then here, the industry switched from the silicon dioxide to hafnium oxide at this technology node. And hafnium oxide is around 20 in terms of the dielectric constant. So it's a higher K value for the gate oxide. That's why this is called high K material. And then this high K material needs to be compatible with this metal gate. So here this gate, if we use silicon dioxide before, it was mostly the doped silicon as a gate metal. But if we use the hafnium oxide, then we have to switch to other metals for the hafnium oxide. So it's a compatible high K and metal gate stack used to build this MOS structure. So this was the innovation at 45 nanometer node. And with this innovation, we can increase the on currents, and also we can reduce the gate leakage. So we can have better capacitor, therefore the tunneling in the logic transistor is suppressed. So we talk about the gate tunneling into the gate stack in the flash memory in the last lecture. But that was used for the memory operation. For the logic transistors, you don't want that to happen. Therefore, you have to increase the gate capacitance and make the higher K value. Therefore, you can use larger thickness to have the same capacitance. And then you can reduce the gate leakage. So this is what needed for the advanced CMOS technology node beyond the 45 nanometer or 28 nanometer. So after that, the new later technology nodes always use this kind of high K and metal gate as its gate stack. So this is one innovation, and then another breakthrough was this FinFET structure, and we are going to spend quite a few slides today to talk about the FinFET. So the FinFET was introduced by Intel at 22 nanometer node, and the other foundries like TSMC followed up at their 16 nanometer node. So the FinFET basically enables the scaling from the 22 nanometer node down to today's 5 nanometer. So this is what we can call FinFET era. And this is for the past 10 years, around 10 years. The FinFET dominates the transistor technology. And we will discuss the more details in the next couple of slides about the FinFET. And then beyond the 5 nanometer, then industry is talking about 3 nanometer and 2 nanometer and possibly beyond. And there's a big question mark here. There's no consensus from the industry what kind of transistor technology will be used for the 3 nanometer and beyond. So there's a rumor that the stacked nanowire or stacked nanosheet will be used in 3 nanometer and beyond. And like Samsung and TSMC both have plans to use this stacked nanosheet or nanowire. And we are going to briefly discuss about this structure as well. This is not happened yet, and we will see that maybe in the next 2 or 3 years. So this is the historical perspective about the scaling. Any questions? Just a quick question about the final. Roughly how many questions can we expect on the final, given that is cumulative? So you will have 5 questions as before. So the total length of the exam will be similar as meter 1 and meter 2. So I would expect that within 2 hours, you should be able to finish all the questions. But most of the questions will be the materials after the second meter. You may have 1 or 2 questions before the second meter. Okay, so then let's move on. So here a quick recap about the MOSFET IV. We have learned that in great details in the 3030. So here we have the ID versus VDS, and this is the output characteristics. And we have group of curves according to different VGS. And then here we have the saturation voltage, and you know this part is the field or the linear region, and this part is the saturation region. So here one of the challenges or one of the non-ideal effects of the transistor is the no longer saturated currents. So this is not desired for a good transistor. You want the current to be flat in the saturation region. But due to the channel length modulation effect or the Debye effect, as we discussed earlier, the current keep increasing with the drain voltage even in the saturation. So this is not good, especially will be amplified into the short channel devices. And the other thing is the IDVG, and here we have the threshold. And here the challenge is in this part, the subthreshold region. Of course, in the linear scale, this is too small. You cannot see anything. So that's why you have to draw the drain current in log scale, in this log scale ID versus the gate voltage VG. Then you can see what's going on below the threshold. So here this is threshold, and then this is log scale of the drain current. So we see the subthreshold slope. And that is defined as decreasing the current by 10 times, the voltage you need to decrease is this S factor. And the intersection here will determine the I off, the off current of the transistor. That will essentially determine the leakage power in the standby or the sleep mode of the circuit. And here the S factor is actually inverse slope in this plot. It has two components. The first one is the gate voltage over the surface potential, and then the second is the surface potential over the log scale of the drain current. And eventually we can express that into this equation that is also in the equation sheet. So the second part are some physical constants. So here KT over Q is the thermal voltage, and at room temperature is 26 millivolts. And then this natural log 10 is when we convert the scale from the log base E to log base 10. So you have to do this conversion, and this is 2.3. So when you multiply by this, then it's about 60 millivolts. So that's why here this S factor is always larger or equal to 60 millivolt per decade. And this first part is a coefficient around in front of the 60 millivolts, and this one is always equal or larger than 1 because it's 1 plus something, and this something is CDM over COX. That is the capacitance ratio. So here, what is this COX? COX is the gate oxide capacitance, and this is the, you have the gate, and then you have the oxide, and then this oxide will give you the COX, and then we still have the depletion width in the channel, and that will give you the CDM. So it's two capacitors, like COX and CDM, from the gate to the silicon substrate. So we want larger COX, smaller CDM to minimize this CDM over COX. So we need much larger COX than CDM. If you can satisfy that, then this term is in the bracket approach to 1. Therefore, you can approach 60 millivolt per decade. So here, this is another reason we want to increase the COX. Right? If you increase COX by using the high K material, then you can decrease the S value close to 60 millivolt per decade. So we care about this S factor because this S factor determines the off current. If the S factor is larger, if this is 60 millivolt per decade, then the S factor like 80 millivolt per decade may have the slope like this. Therefore, the I off current will increase exponentially because this is in the log scale. So the S factor will determine the leakage current, therefore the standby power. And the S factor, we cannot do too much about that because the second part here is physical constants. And the only thing is the temperature here you can change. Unless you cool down your chip or build it in Alaska, then you cannot really do too much about the temperature. And the first term here represents the gate to channel coupling because this is the gate voltage and surface potential is the potential of the channel surface. So here, this is like a gate to channel coupling, how much gate voltage you apply and how much percentage of that gate voltage can be transferred to the channel. So this is the gate to channel coupling. A good transistor should have a strong gate-to-channel coupling. Therefore, you can minimize the S factor. So any questions so far? Those are like the key concepts from the previous discussions. And then this is the structure of the conventional bulk MOSFET. This is the device structure we talked about so far in the 3030. And you have learned this before. So this is like a schematic of the transistor structure. And we call it bulk transistor. This is the silicon's bulk. You have the silicon substrate. So it's like the bulk of the substrate. You build the transistor on top of the bulk at the surface. And also it's called planar structure because here the channel is at the surface of the silicon. So it's a planar structure. This is like the channel, the surface of the silicon. And then this is top view of the layout where you can define the gate length and the W width of the channel. And here you see those contacts with the source and drain terminal. Those are the metals connect to the top level interconnect. So this is what we discussed so far. And then what are the problems here for those transistor structure to be scaled to advanced gauge load? So the major challenge here is this short channel effect. If you simply scale the length of the gate or the channel, then if you simply scale this length, then the short channel effect will take effect. So what is the short channel effect? Short channel effect basically says that the transistor's gate lost the control of the channel. Therefore, the drain voltage can affect the current. Ideally, the transistor should be the gate-controlled device. The drain should not affect the current. Then you can get the perfect IDVD curve. The saturation region will really saturate because the drain voltage, once you reach the pinch off, then the drain voltage will not affect the current. This is true in the long channel device. So here we show the band diagram of the EC, the band edge of the conventional conduction band. And then you see the green curve. This is the long channel. So when you apply the VDS, it will not affect what happens from at the source to the channel barrier. But if the channel is short, here you see this drain voltage will affect this source to channel barrier. For example, here we show this VDS dependency. For the non-channel, if you change the VDS from 0 to the power supply VDD, then you push down the band. Then this, because this is none, so what you change here will not affect as a source to channel barrier height. Therefore, the current will be the same because this barrier height determines how many carriers, electrons, can flow into the channel. But if the channel is short, like this red one, then when you increase the increase the drain voltage, then the barrier height will be reduced as well. Then the larger current will occur when you have larger drain voltage. That explains the not saturated drain current, right? So this is IDVD. So this drain current keep increasing because as you change from 0 to VDD, then this height is going to be reduced. Then you have larger currents over this barrier. Therefore, the currents will increase. And also from the subthreshold node point of view, when you change the VDS, then you have more current over this barrier. So even the gate is gate voltage is small in the subthreshold region, then the subthreshold current will significantly increase due to the drain voltage. So here we show that as for the short channel, you see we have two curves. So when the drain voltage increase, then the curve will shift to the left. As a result, the I off will increase. As I on will also increase a little bit, but mostly I off will increase because this is in log scale. So here, a small change actually means a large factor of drain current change. So this is the short channel effect. To summarize, ideally, transistor should be a gate-controlled device. Drain voltage should not change the current. This may be true for the non-channel device, but for the short channel device, because drain is so close to the source, you change the drain voltage, it will affect this source-to-channel barrier. Then the current will be affected by the drain voltage. That means this transistor is no longer purely gate controlled. Also, drain will control the current. This is the key challenge for the transistor design at short channel below like 50 nanometer. So this is the problem. And for scaling, our goal is to increase I on and decrease I off from generation to generation. Why? Because from the performance point of view, you have learned that in the digital circuits, like the inverter, the delay is proportional to the capacitance load times VDD divided by the I on. So if your on current increase, delay decrease, then the circuit can run faster. And then the leakage power, of course, this is total power. You have the standby leakage power and then the dynamic power. So for the leakage power, then the I off will matter. So you want to minimize the I off to reduce the total power. So always you want larger I on and smaller I off. But this may not be achieved at the same time. Why? For example, here you see we change the VDS, both I off and I on increase because the curve shift to the left. Then both here I on increase and I off increase. So there is a correlation. That's why in here, this is the data from Intel 45 nanometer process. We show here the I off in the log scale and I on in the linear scale. So here at the same technology node, actually we have different combinations of the I on and I off. In other words, we can have different flavors of the transistor at the same technology platform. So why is this important? Because that can provide some flexibility in the circuit design. So here, for example, if the transistor is operating at this point, so this is relatively high I on, like 1.4, and also 1.4 milliamp per micrometer. If the width is 1 micrometer, then the current is 1.4 milliamp. And then here the I off is relatively large. It's like 100 nanoamp if the width is 1 micrometer. So this is called the HP transistor, high performance transistor. Because if you use this transistor to build the circuit, this circuit will be high performance because your on current is relatively large. Therefore, you can run the circuit faster. This is good for high performance computing. For example, in the data center, if you build the server processor, you want to use the HP transistor. So the trade-off will be the larger leakage current. But in the data center, because you keep running your chip, then the leakage actually relatively will be less significant, because most of the time you are in the active compute mode in the data center, and you want the performance. On the other side, if you are designing the mobile device, you want to use LP technology. LP transistor, low power transistor, which you will sacrifice the on current a little bit from 1.4 maybe to 1.1 here. But the leakage current will be reduced significantly. This is in log scale. So it's like 10 times reduction of the leakage. This is important for the mobile devices like your smartphone, because the battery time is important. You don't want your phone to drain the battery within 1 hour, right? So if you use high performance transistors, then probably you will end up with only 1 hour lifetime per charge. So this is the trade-off. You can sacrifice the performance a little bit, because in your mobile phone you're not going to run the big programs there. So what matters is the lifetime for the battery, which will be affected by the leakage power. So each foundry will provide different transistor technology, even at the same technology node. You can have different flavors of the transistor to design the chip. And then the scaling from one generation to another generation, for example, here 45 to 32 nanometer, the goal is to shift this curve to the right. And you see here, you have to fix some criterion here. For example, here if we fix the off current to be this 100 nanoamp per micrometer, then from 45 nanometer to 32 nanometer, then the on current here will increase by 14%. This is at the same off current. And then if you fix the same on current around 1.4, then the leakage will be reduced by 5 times. So this is the benefits for the scaling. So either increase the on current or decrease the off current. So you have to make some trade-off depending on your design is high performance or low power. But overall, the trend is moving to the right. Then you are going to gain the benefits doing the scaling. So any questions?